Had what happen?
where you graded a test and then there were several issues to grading, so you had a mob of students appear outside your office.
What I like to do is I like to just take them, staple all the tests together, and just fling them. And then what I do is the one closest to me got an A, and the ones closest got an A, and then as I go further, I use the radius. I measure it with a ruler, and then I use the ones in the back. Had reason they fell to the back is they were loaded with stuff, and I figured they didn't know what they were doing, so yeah, and everyone was so confused they just sat there. And so I'm just making this whole up. I'm not. I hear you talking. I'm not making fun of your plight. I'm in this mode. What happened to me is ever since I found out about that CAD thing, and I've been asking questions, and I'm still confused. And so,
You're about to have like 30 students come to his office now.
oh really? Well, he's lonely. I don't know who it is. I don't want to know, but he's lonely, so you need to go.
There's like certain kids, like some enrollment,
I'm sorry.
and some people got hit on 5 points, some people got hit on 10, some people got hit on 15. It just depended on.
Well, what it was is he used his hand and he flung it like a frisbee. That's why.
Some people don't even get cameras.
Anyway, okay. Okay. Okay, so I'm gonna do a little dynamics today. So I'm gonna just pick a problem. I'm gonna make up a problem that's kind of straightforward, and I'm gonna run through something else and do instant center and the other method, but I'm also gonna add the acceleration. So here we go. So here's A, here's B, and I'm going to make it kind of simple in a sense and just lay it over here, and here's C. And this is just a piston. So what I'm doing is, and I don't want to deal with any angles. I don't want to deal with any of that stuff. So what I'm going to do, I'm going to put the coordinate system here and here. And I'm going to say, I'm just going to make this up. The X location of B and the Y location of B looks to me, I don't know, 5 and say 4. How about that? Looks good to me. Or actually, how about 4 and 3? Because that gives me let's do it this way. 4 and 3. Then it's a 3, 4, 5. Then I'm going to pick the location of C, and I'll just say X equals to, now I want to make sure in good design, you want to make sure that it's long enough so it doesn't get pulled back and hit. But I'll just say it's, how about 15, and Y is equal to 0. So you got this thing measure. If I put a ruler on it, what you'd see is this is, a dimension. Say it's in a CAD program, that'd be 15. This would be 5, things like that. However, I'm trying to make my life simple by using these and not using angles and stuff. So, the velocity of B is equal to the velocity of B relative to A plus the velocity of A. And so you also know that's equal to 0. So you can find the velocity of B from a standard IJK, and I'll write it over on the side. Oops. Okay. Equal omega AB cross R B to A. So I guess if I'm doing this, I need to specify what the omega is. So I'll just say omega is equal to 180 radians per second. Now, over on the side, if I give X and Y, then this means this is plus, you do the right hand, you lay it on X, you rotate to Y, and your thumb comes out in Z. So that's a positive omega. So it turns out from a vector standpoint, this is plus k. So here. So if you look at it, this, I'm just highlighting it because that has a vector component to it. And sometimes that's not completely talked about enough, I think. But so if I put this in here and I'm putting in the omega, first I get 180. Maybe I should have used another number because now that I got it big, I'm going to have to multiply a big number. Do y'all mind if I change that 180 to something like 10? Because I can easily multiply 10 times a number. Is that okay? So I'm going to change that to 10 because I know how to multiply 10 times a number. I don't have to waste time with that. Now, go in and take this vector. Okay, so now this vector is a vector that points to B, originating from A. Hey, and that is actually just 4, 3, and 0. So if you're looking at the velocity of B, it's nothing more than I, which is, I'm just going to write down 30I minus 40J. Okay, there we go. Okay, so I just looked at that, and here's what happened in my mind. I did this minus that. Uh-oh. I made a mistake, didn't I? So, actually, should be minus 30I. Now, did I do a mistake on the other? I do a minus sign because of that. That number times this number minus this number times that number. And so, in fact, I did an incorrect E there. So it turns out that makes sense. The velocity vector should look like that, going in the positive Y, the negative X. So I'm okay there. The reason I'm doing this is I'm laying down a pattern, and then I'm going to slide the sheet over and work off of the pattern, zooming in and zooming back out, and we'll see the accelerations mimic exactly this same thing. And so in that light, I think I'm going to do them each at a time. So what I'm going to do now is I'm going to take a little block, and then maybe I'll do it under it. Well, let's see. Maybe I can do it under it. So if you look in the text, you've got the acceleration of B equals to the acceleration of B relative to A plus the acceleration of A. The difference here, and I'll sort of express this one becomes alpha cross RBA, and this should be AB, which it looks a whole lot like that. But it also has a minus omega AB squared RB to A. And then, of course, I got the acceleration of A, but I already know that's 0. So let me sort of, and I'm going to do it on this one first to kind of describe it. Kind of like this. Okay, hang on. Let me roll down for a second and use the old car here. The car mentality. I've mentioned that before. You're in a car. You're out in the parking lot. There's nobody else there, and if there is, they'll get run over. So you're driving around in circles like crazy. You're doing the best you can to keep the radius fixed. Now, when you're starting to drive, of course, as you're going around in circles, you feel yourself being pulled to one side of the car. So you're using the steering wheel. So you've got like an acceleration that's coming in. Now, usually it's V squared over R, but that's the same thing as omega squared R, because why? V is equal to omega R. And if you came back in here, took that out, and then you said, well, V is omega R, squared over R. Oh, well, that kills off one R down there, and you get omega squared R. Well, it's not too surprising. That's exactly what sits right there. So in fact, you could kind of say that this term is result of you using your steering wheel and going around in circles. Now, what is this acceleration? This acceleration is as a result of you starting from dead still and you're speeding up. You're going faster and faster. And the alpha means you're changing omega with respect to time. So you initially started real slow, and then pretty soon you're going faster and faster, so you're spinning up. By the way, there's a lot of, okay, so here's the difference. There's a couple of differences between mechanicals and electrical. You've got to take, well, one, you've got to take some circuits that has to do with, do you have to take circuits too?
Yes.
Okay. So when you get into circuits too, you have J omega. Oh, has everybody had that yet?
Yeah, well, we're right now.
Okay. So there's a big split right down the line in which I think they should add something to circuits too that applies to mechanicals. And I bring this up and I'm kind of diverting because when you turn on a circuit, you go in and you flip a circuit, usually the delay time from you to hit that switch for it to be reaching its frequency is very slow. I mean, very fast. In other words, you flip it and it's basically doing like this, right? And so they're running around E to the J omega T and everybody's figuring all this stuff out. Y'all done that yet? Add this and do. Well, this is all steady state response. And in electrical, it's okay because the transients are so quick and they're insignificant because the voltage are so small that it doesn't really matter. And the reason I bring this up is, say you put an electric motor right here and you have a rod connected to it and it has a piston and it's going around and around. When you flip that switch, there's a mass there associated with this, associated with that, and with that. Usually you're drawing current out of the wall. And so what you'll find with omega is instead of omega being a function like this, in electrical, omega goes bzz, and you see a small transient and it stays like that. In mechanical, you can see omega doing like this, taking some time to reach steady state. So this means your transient is much larger, and the effects of the transient in a mechanical system are this, and you could say it pretty easy. Take a 5-pound thing, set it on a table, the table deflects. Take it up higher and drop it, and the transient, or the minute it hits that table, it acts as though it's a much heavier weight. The transients give you a much heavier load, and therefore can break things much easier than a static situation. So this concept, really the way it should be done, and of course, I'm diverting. Why am I talking about this? Anyway, I just got the sidetrack. But anyway, when you get into Laplace transforms, have y'all done that yet? Okay, so now Laplace transforms actually have the transients in them. And if you think about what you actually did in differential equations, remember they had the particular solution and the homogeneous solution. Remember that kind of stuff? Did they? So the homogeneous is that when there's a zero on the right-hand side, which is just basically free movement, and then the other is forced movement. If it's forced movement and you have no homogeneous solution, the homogeneous is usually the transient. And then the other one, the particular, is usually the steady state. So when you're doing J omega, you're ignoring all the steady state. When you start replacing the J omega with S, you can back it out and get the transients out of there. It's harder to get the transients, but the transients are kind of important. And the reason I diverted like that is because I started thinking, well, you know, when you're in the car driving around, you don't just instantly start at a certain frequency. You have to build up to it. You started at omega equals to nothing, and then you had an alpha. And so you're building up speed here. So this alpha is related, related to the gas pedal or the brake. So as you push the accelerator, alpha increases. If you're going at constant speed, alpha is nothing. If you're putting on the brake, you're slowing down, so alpha is something. And so that being the case, I have to come back and now say, is this guy or this thing having an alpha? Is it speeding up? And in order to have a complete problem, I need to say something. So how about 2 radians per second squared? So I'm just going to make it 2 because I have a pretty good ability to multiply numbers by 2 and 10. But outside of 2 and 10, I can't do anything. So let's solve this problem. Okay, hang on. Come on, what's wrong with you? Let me get these things out of here. It's not going anywhere. Okay, so let's look at this now. So if I want to know the acceleration of B, I end up with this term, which looks exactly, and this is the point here, 0, 0, and 2, 4, 3, and 2. And then minus, what was my omega AB? It was 10, right? So the magnitude was 10 times 4I plus 3J. Now, let's look at each one of these terms. And I'll shrink it and move it so that we can look at each term. This is the reason I like to do them in parallel or do one right after another. If you look at this analysis, you realize I just took the omega, I stuck it in a row, I took the vector, which went from here to here, which is 4, 3, and then I multiplied it out, and hopefully I didn't make a mistake. If I stare at this enough, you'll notice this is almost like that with one replacement, and that's this. So if you did this right, you just look up the page, which is exactly what I did when I wrote the last row. I just looked up here, I copied that, and then I replaced that with alpha. So when you're doing that, you could do them one after another, but I was initially thinking when I came in the room, I was going to do this over to this side, but then I realized if I shrink it way down, it's kind of hard to read. So this way I just do it under and I can see both. Then I look up here and I see this number sits right here. It's a scalar now. It's the magnitude of the omega, and you just square it. It's the same thing, you know, the v squared over r, or the omega squared parentheses r over r, or omega squared and then r. The reason the minus sign's there is because he shows you in the book that actually this acceleration at this point is pointing back this way, the opposite direction of that. And its magnitude is that vector length times that. So if you just take that vector length, I mean that actual vector, multiply it times omega squared, you get that. Now to me, when I see this, I look at the bottom row and I repeat this, 4, 3, and then there's nothing. Now if we look at the numbers in about 5 seconds when I can roll down the screen, what you find is, okay, I do an I, now I do I, this number times that number, but it's a minus, so I can do 3 times 4. I know how to do that. So I get minus 6I, and then the other one, I take a minus j. Why did I put a parenthesis? Well, I'll leave the parenthesis. I take a minus j, this number times this one, minus that one times that one. But it's already a minus because I got that one, so it ends up with, okay, 8j. Okay. Oh, shoot. Here, I know. Here, can I get rid of that? Oh, yeah, good deal. Now, over here, I get a minus. Okay, so let's take a look at figuring out this. I get 400I minus 300J. Now let's look here. Let's look at each of these terms and see what you get in a vectored form. I wish I had done omega a little bit smaller. And I don't, now I'm really apprehensive about going back and changing that, but it's okay. We'll do it this way. Okay, let's look at the link A. Goes up here. Here's point B. Okay, so if I draw this vector, should be like that, where this thing goes backwards 6 and up 8. And so it's perpendicular to the line that goes from A to B. Now, if I redraw it again, because I don't want too many things on the same drawing, what you'll see from this term, it's minus 400I, so it goes back 400, and it goes down for 300. And it turns out that it exactly follows this link. So it, in fact, is the V squared over R kind of thing. Now, if you ever, okay, some checks. If you ever, okay, and you will be, because there's gonna be several of these on that take-home portion, which I promised I was in it. But now I think what I'm gonna do is I'll give it to you next week, and I'll just make it due after spring break. We'll do the in-class portion before, and then a week or so after spring break, we'll make that other part due. Let's look at some checks here. And these checks are kind of interesting. Let me show you the checks, and then we'll talk about how these checks actually work. And they're kind of convenient. First of all, maybe I should do the checks, do the first check back up here. So here, let's do the first check up in here. I got a little bit of space right there. There's something interesting here that occurs, and I got just enough space, and I'll put it right in here. Hey, but I'll color code it. So here, we'll make it green, just because it keeps me awake, at least until lunch. Okay, so if I take this vector, just this one, and I'll just call it vector A. Now, you know that it's the velocity of B, but I'm going to call it vector A. Vector A dotted with, oh, here I got this one. Let's dot it with R, B to A. What do you think I should get? Well, if you dot it, you'll get minus 30 times 4, this number times that number. Add that to this number times that number. And technically, I need to do it with a z, but there is a 0 here, and there's actually a 0 on that one too. So what you get is plus 3 times 40 equals to 0. Now, is that an anomaly or is that a fact? And it turns out, if you stare at this, and let's look at a general sense here. You take a vector, let's just say you take any old vector A, you cross it, or here, I better use a different term because I already used the letter A. So here, take any old vector B, cross it with C, I get a result, say D. Then I dot it with B, and I dot the result with C. What do you think by nature those should be? Let's look at it geographically and just say, got a vector B, don't care where it's at. Got some other vector C, don't care what it's at. I cross them. Essentially, what you're doing is you're taking a plane of two vectors. So you got two vectors sitting out there. I don't care where they are. You take your hand, you cross them. Is this vector that comes out of them perpendicular to this one and this one? Every single time. They're always going to be 0. Now, that's a fact from vectors. And to me, that's a great fact because now I can tell you that every single time I get a result here, I can dot it with this one and it should yield 0. I can dot it with that one. It should yields 0. If I dot it with the top one, that's useless to me because, yes, in fact, 0 times this is 0, 0 times that is 0, 10 times 0 is 0. That's, who cares? This one is where I usually can make my mistake. Let's say I made a mistake and I ended up with a plus right there. So I look at it and I'm thinking, oh, I got the right answer, and I keep working the problem and everything blows apart on me later. Or do I want to stop right here? 4 times 30 plus 3 times 40, that's 240. So by just looking at that, and that's convenient because I always list them right under there, so I can look right here, look right there, multiply them, uh-oh, something's wrong. And so that vector, you know, that cross dotted, the result of a cross dotted with either of those vectors being a 0 gives me a chance to check my work as I go through, because that can't be. Uh-oh. Or say I copied the number down wrong and I had that. So immediately I got a problem. So there is opportunities through all this work to check as you go along using that. So you can check it here. You can check it down here as well. So you do that. Okay, so what's minus 6 times 4 plus 8 times 3? Minus 6 times 4 is minus 24. Isn't 8 times 3 24? So they both knock each other out. Another interesting fact, do you think this one is perpendicular to that one? You have to remember, this vector is the direction. That vector is the minus of it. If I took two vectors in a plane and I took the minus of it, it's still the same plane. And so if I take the perpendicular, which is crossing it, it's always, so this should be perpendicular to that every single time. Minus 6 times 400 and an 8 times a minus 300. Well, minus 6 times 400 is 2400, I think. Minus and a minus, I got a plus. A plus 8 times minus 300 is a negative 2400 again. They knock each other out. So once you check this one off of here, you can turn around and check this one off of this one. And then you have the confidence to just keep going. It happens every single time. There's something there along the way for you to check. And it basically is that cross product with the dotting the result with either two of the vectors that gave you the cross product. So, so that's why math is your friend. So, okay, so does that all make sense? I'm trying to think of a way of, because here, let me tell you what, let's see. Oh, is it not working? Uh-oh. Oh, it is.